Thanks a lot to the organizers for putting together this wonderful conference and workshop, and for giving me the chance to speak. I'm going to be talking about some work in progress with Sanjay Mudgalia and Tibor Rakovsky. So the subject of this talk is the general process of thermalization in chaotic quantum many-body systems. And thermalization is a ubiquitous phenomenon. We observe it constantly in our everyday lives. And for the purpose of this talk, I'm going to define it more precisely as follows. That suppose you start with some initial state psi 0 in some chaotic quantum many-body system. Then you evolve it with the chaotic many-body Hamiltonian H and obtain the state at some late time t. And it turns out that in this state at late times, most details of the initial state are forgotten. And from the perspective of many observables, this time-evolved state psi of t essentially resembles a thermal state, like e to the minus beta h at some temperature. Okay. While this is a process that we take for granted in our everyday lives, it's actually very difficult to understand how it emerges from any given microscopic dynamics. And this is because it takes place precisely in a regime where we have a very large number of degrees of freedom and strong interactions between them, so that we don't really have analytic control in most situations. And one type of system where we would particularly like to understand this process is a holographic CFT, where thermalization in the boundary corresponds to the process of formation of a black hole in the bulk. And so understanding the mechanism for thermalization in general chaotic systems can also provide some insight into the process of black hole formation from a microscopic perspective. Okay, so the general picture we have in mind is that under the time evolution of a system with local interactions, we find that with time, increasingly large regions in the system start to become thermalized. So at some relatively early time, you can imagine that each of these small regions looks approximately like a thermal state, and then the size of the regions for which this is true grows with time. And for some fixed region A, we can understand this by saying that the reduced density matrix of the time-evolved state in that region starts to approach a thermal density matrix or become close to a thermal density matrix. And one way to probe this is by looking at these quantities called the Renyi entropies involving this particular function of the reduced density matrix. So these are defined in this way for different n's, and the n going to one limit is the von Neumann entropy, which, as was reviewed in previous talks, has the best operational interpretation. But to understand the overall structure of the density matrix, it's useful to understand all of these moments. Okay. And so the statement is that starting from some small initial value in some say initial product state, as the state starts to look more and more like a thermal state, the value of this quantity will grow and eventually approach its extensive value at late times, extensive thermal value. Okay. Good. So it turns out that there is universality not only in this late time value of the Renyi entropies, but also in the way that this late time value is approached. And it turns out that in a lot of different chaotic systems, if we consider sufficiently late times and sufficiently large regions, a certain formula called the membrane formula turns out to be a very good description of the evolution of the entanglement entropy. So this was originally proposed in this paper based on studies of Random circuits, but it turns out to be true in a variety of other systems. So let me take a minute to explain what this formula is. So suppose we want to understand the time evolution of the entanglement entropy of this region A, and this is in 1+2 spatial dimensions. So we now imagine extending the system from tau equal to t to tau equal to 0. So we now turn it into some slab with a time direction. And we consider all possible two-dimensional surfaces in this case, starting at the boundary of this region A. Okay, so we label such surfaces by n. They have two coordinates which parameterize them. So it looks a little bit like a string worldsheet, and I'll mention towards the end of the talk that this might actually be a useful way of thinking about it. So now at each point on this surface, you have some velocity vector, which is related to the angle that it forms with the vertical direction. And the statement is that the time-evolved Renyi entropy is given by the minimization over all possible such surfaces of this object, where we integrate over this surface some velocity-dependent function, which I'll call epsilon. And we also consider the initial the region A prime, which is projected by the surface on the tau equal to 0 slice, and add to this expression the the value of the initial entropy in that region. Okay, so this is the quantity that we want to minimize, and this function epsilon n has this kind of form where it's some even function of v. It has a minimum at v equal to 0, and it has to satisfy some non-trivial constraints.
Is v function on the boundary of A?
No, v is a function all along this surface. So yeah, sorry. So this surface is starting from the boundary of A. So in this two spatial dimension setup, once you extend it in the time direction, this is some two-dimensional hypersurface, and v is defined all along the surface.
Thank you.
And we're only interested in the absolute value of v in this expression. Okay, great. Any other questions about the formula or the notation? Yeah, good. So, so this is a general. So the fact that these two statements have to be simultaneously true at some velocity vb comes from the fact that it's not entirely obvious from this, from just looking at this. But if you work it out, it's clear that if you start with an equilibrium state, like some thermal density matrix, then it should just not evolve under the evolution of the system. So its entropy, you should just get 0 for this time-dependent term, and that happens if these constraints are obeyed at some vb. And then with some further analysis, like if you can also understand the relation of the OTOC to these quantity to this membrane tension quantity, and from that it turns out that this velocity should be interpreted as the butterfly velocity. Okay, good. Any other questions?
Sigma tau refers to the surface of the boundary.
Oh yes, sorry. This is a typo, so it should be m in my new notation, but yeah.
M.
So m is this membrane, and
okay.
I consider all possible choices of this.
So it's m rather than sigma tau.
Yes, yes. Thank you. Good. Okay. This was, as I mentioned, originally motivated by studies in random unitary circuits, which can be done most explicitly in 1+1 dimension. Yeah, these groups propose that this is a more general formula. And indeed, it shows up in a very, so let me first mention some simple consequences of the formula that I wrote down on the previous slide. So if we just consider the case of an initial product state in 1+1 dimensions, and suppose we're considering the entanglement entropy of a single interval. So in this case, the membranes are just lines which pass through this space-time diagram from tau equal to t to tau equal to 0. And it turns out that in this minimization, you essentially just need to minimize between two configurations. One where the lines just go straight down with v equal to 0, which makes sense because this function had a minimum at v equal to 0. And another configuration you can consider is when the membranes combine together at some intermediate time. And it turns out that there's some competition between these two diagrams, which tells us that the entanglement entropy grows linearly and then eventually saturates at a value proportional to the volume, which is exactly the thermal value. Okay? Good. So, and then in this case, we only needed the value of the membrane tension of v equal to 0, but if we consider more general situations, then the form at other velocities is also important. So a question we can ask is, what is the physical origin of this membrane formula, and in particular of the velocity dependence of this function in general systems? And this is a question that I'll try to address in this talk. And one remarkable thing is that you can also derive this membrane formula in holographic thermalization setups. So as I mentioned, thermalization in the boundary is dual to gravitational collapse in the bulk. And this HRT formula, which was reviewed in earlier talks this week, allows us to find boundary von Neumann entropies of some region in terms of some bulk extremal surfaces. And in particular, this setup of some quench or some initial thermalizing state on the boundary corresponding to a gravitational collapse in the bulk was considered in these papers. And then these calculations were further simplified and reorganized in this calculation by Marc Mazet, where he showed that if you consider a limit of sufficiently large system size and late times, then somehow we can entirely get rid of the bulk radial direction in this minimization problem and just rewrite this as a minimization problem in the boundary theory. And it takes exactly this membrane form, and he derives some explicit membrane tension. Okay, and that membrane tension satisfied all of these non-trivial constraints that I listed on the previous slide. And it turns out that it only depends on some universal things like the properties of the late time black hole metric that is formed in this process. Okay, so a question that it would be very nice to understand is what is the underlying structure in the boundary CFT that leads to this kind of picture. This is not a question that we'll be able to directly address in this talk, but hopefully we'll have some hints of the answer. Yes?
So in these random circuit way of getting the membrane picture, was there some analog of large N, or just works even for small n?
No, it works without any large N. Yeah. Yeah. Okay. Good. So the challenge is that if we consider the evolution of the nth Renyi entropy and its time evolution in some general quantum many-body system, then we get a very complicated Lorentzian path integral on 2n copies of the system, and there is no easy way to analyze this in general systems. But what we'll do in this talk is restrict to a certain class of Brownian models, where we'll find that we can replace this Lorentzian path integral with the Euclidean path integral on 2n copies of the system. And somehow, now that we have a Euclidean path integral, it's much easier to analyze. Okay, and so we'll analyze some general features of this Euclidean evolution, which will allow us to recognize certain low energy modes which are responsible for the membrane picture. And the hope is that once we phrase things in this language, then this might be generalizable to setups that we want to understand, like chaotic quantum field theories. Okay, so let me more specifically introduce the models we'll consider. So we can make, we have in mind some kind of lattice model in arbitrary dimensions, and we can make some choice of local operators H alpha, which couple nearby sites. And next to these, we have some numbers, J alpha t, which of course would be time independent in some realistic system, but we now take them to be IID Gaussian random numbers, which are in particular uncorrelated for different times. Okay, and this turns out, so while this assumption is not very realistic, we might imagine that whatever structure we get from this at sufficiently late times is not too different from what we have in some chaotic system with energy conservation. And in principle, it's possible to choose these H alpha operators to incorporate some kind of other conservation laws other than energy conservation, just by choosing them to commute with some symmetry operator. Okay, and it turns out that in such models, the Lorentzian evolution can be replaced with a Euclidean evolution with some non-negative Hamiltonian. Okay, and the Hamiltonian has this simple general form in terms of whatever H alphas you chose. Okay, so the main thing I want you to notice in this expression is that it's a sum of non-negative terms. And essentially, if I have n forward copies and n backward copies of my evolution, then there are H alphas corresponding to each of those copies appearing in this expression, and all the forward copies and all the backward copies appear in a similar way. Okay? And so now, because we have some Euclidean evolution, if we want to understand the behavior at late times, all we need to do is understand the structure of the low energy states of this Hamiltonian. Okay, so it might seem a bit surprising that we were able to rewrite the Lorentzian evolution as a Euclidean evolution, so let me quickly go through how this happens. So we've considered the set of models where we have some time-dependent Hamiltonian. We've taken these J alphas to satisfy these averages. And then if we consider the evolution for a small time step of length epsilon, we can just do the Taylor expansion of this two-copy evolution for small epsilon. So we get some set of terms like this. And the main thing to notice is that because these averages were 0, the linear terms, when I write this, when I expand this further, will just vanish, and I'll end up with some quadratic terms. And then because this variance is proportional to 1 over epsilon, in the end, I end up with something of the form e to the minus epsilon p for some non-negative operator p. Okay? And then there's a very similar analysis for an arbitrary number of copies. So this two-copy evolution is relevant for observables like just two-point functions, and these can have a non-trivial behavior if you choose the H alphas to have some symmetry. And this was used in this earlier paper to understand how diffusion emerges microscopically from such models. Okay, so our goal in this talk is to understand the second Renyi entropy, and we're now going to write it as some transition amplitude involving 4 copies of the system. So suppose our system consists of some set of sites, each with Hilbert space dimension q. Then one thing that it'll be useful to do is introduce some notion of up and down spins for studying the second Renyi entropy. And if we were looking at the nth Renyi entropy, you would have to introduce n factorial such spins. And these are essentially associated with the 2 permutations in S2. So they basically tell you to associate the states on different copies with each to identify states on different copies with each other in some pattern. Okay, so it doesn't matter too much what these are, but there are two such spins. And in terms of such spins, you can write the evolution of the second Renyi entropy as some amplitude under the Euclidean evolution with some initial state, which is determined by the actual initial state of your system, so this psi 0 state. And then the final state here is if we were considering the entanglement entropy of some region A and its boundary is sigma A, then this final state is a domain wall state around the boundary of the region. Okay, so in particular, it's a domain wall between these kinds of up and down spins. Okay, so this slide is a bit heavy on notation, so any questions? Okay. Good. So the first thing we can try to understand is just the equilibrium value or the late time limit. And all we need to do, if we want to understand the t going to infinity limit, where this object just becomes a projector onto the zero energy subspace, is to just find what the zero energy states are. So it turns out that because of the particular structure of the Hamiltonian that I wrote down, for any choice of these couplings H alpha, this 4-copy Hamiltonian always has at least 2 zero energy eigenstates, which are given by up everywhere and down everywhere. Okay, and if we make some generic choice of these H alphas, which have no symmetries, then these are the only 2 ground states. And so this time evolution operator at late times just becomes a projection onto these 2 ground states. And then putting this into the expression for the entropy that I had in the previous slide, you can see that you get a minimization between these 2 terms, which gives you a sort of page value of the entanglement entropy, which is expected if you have no symmetries and you're thermalizing to infinite temperature. Okay, and maybe for some intuitive interpretation of these 2 terms, so we can try going back to the Lorentzian path integral description of the system. So this had some n forward-going copies and some n backward-going copies. And so in particular, you can write this as some path integral, and then the action has, in the exponential, some plus IS's associated with the forward copies and minus IS's associated with the backward copies. And it's natural that if you consider very late times, then one thing you can notice is that there is a certain set of configurations here for which the space factor just vanishes for all times, which is if you identify each forward-going copy with some backward-going, the phi's on some forward-going copy with the phi's on some backward-going copy. Okay? And the number of ways you can do this is exactly associated with the number of permutations in Sn. And you can imagine if you have some chaotic system, then at late times, all the remaining contributions are just very wildly fluctuating and cancel out. So it's natural to get some projector onto states associated with permutations at late times. And this can be seen as some explicit realization of that. Okay, but our goal is now to understand the approach to the equilibrium value. So we want to understand the low energy excitations of P4. And in general, for general choices of these H alphas, P4 can take you out of the subspace of these up and down spins into into the larger n-copy Hilbert space. But the first thing we can do is just project the full Hamiltonian for any choice of H alphas onto the up and down subspace. And this gives us some universal spin half Hamiltonian. Okay, and we can make some further simplifications. So we'll first consider one spatial dimension and the large Q limit, where again Q is the local Hilbert space dimension. And then essentially the effect of this Hamiltonian, P4, is just to move domain walls either one step to the right or one step to the left. Okay, so this turns out to be very easy to diagonalize. And we get some band of lowest energy eigenstates, which are just plane waves of domain walls between down and up spins. Okay, so they're characterized by some momentum k, and they have this form. And you can see that the dispersion relation associated with them has this form of 1 minus 2 over q cosine k. So in particular, because we're considering large Q, this dispersion relation has a gap above the 2 degenerate ground states, and then the eigenstates look like domain walls. Okay, and this structure is now immediately enough to see the emergence of the membrane picture. So if we plug in these eigenstates and eigenvalues into the previous expression for the entanglement entropy, and we consider the entanglement entropy for some region, say to the left of some site y, so this entire half line, then plugging this in and doing some further simplifications, we end up with the sum over all velocities of this object, which involves an exponential of minus log q times the membrane tension times t, and some contribution depending on the initial state. Okay, and this function epsilon v is just the Legendre transform of the dispersion relation. And so we can see that at late times, we just want to find the maximum value of this exponent, which corresponds to minimizing between this object for different v's, which is exactly the membrane formula. Okay. And so this was the band of lowest energy eigenstates, and then you can also consider the subspace with some n domain walls, and it turns out that there's again a very simple structure. So you find that the eigenstates within the subspace with n domain walls are just antisymmetric combinations of essentially products of plane waves of single domain walls. So this dx1 through xn is supposed to say that I first start with all downspins up to x1, and then I have some upspins up to x2, and so on. Okay, so these are some natural multi-particle excitations, and it turns out that their energies are additive. So in this sense, they're non-interacting, and they're essentially almost like free fermions, except that in writing this expression, I ignored some interactions which can cause domain walls to combine and annihilate in pairs. So you can go from the n domain wall subspace to the n minus 2m domain wall subspace for any n. And once you take into account this set of interactions, the energies are still additive, and you get some correction to the eigenvectors. But taking all this into account, we get the membrane picture for essentially arbitrary numbers of disjoint intervals. And this is nice because we've sort of phrased the whole problem in terms of some essentially non-interacting particles, but we should note that this picture is very different from an earlier sort of quasi-particle picture for entanglement growth, which was phrased in a very different way. In particular, these particles that we're considering here are non-local in a certain sense because they involve domain walls, and the role that they play is very different. So in particular, if we consider the entanglement entropy of multiple disjoint intervals, then in the quasi-particle picture, you can have situations where the entanglement first increases and then has some dip and then goes back up, which you should not see in a chaotic system. And the membrane picture is consistent with the fact that you should not see this. Okay? Any questions about? Okay. Good. So far we were in some very special limit of the one-dimensional model, and now we can ask what happens when we go away from this limit. So now there are actually some interactions which can cause a single domain wall to split into three and then split an arbitrary number of times. So in principle, this picture can change a lot. But in order for this membrane picture to still hold, we need two things. So one thing we need is that the spectrum should still be gapped, and there should still be some well-defined single particle band above the gap. Okay, and this is a bit hard to see by just going order by order in perturbation theory in this Q parameter, but one thing we can do, because we just have some spin half system in one dimension, is explicitly diagonalize it. So we can explicitly check that there is some well-defined one particle band at small momenta for essentially any finite value of Q. Okay, and in the language of Shuheng's previous talk, this is related to the fact that this model, I didn't write down the Hamiltonian explicitly, is in the same phase as the symmetry broken phase of the transverse realizing model. Okay, it's not quite the same as that, but it's in the same phase. Okay, but we actually need something stronger. We don't only need that there should be such a band, but we also want the eigenstates in that one particle band to look like plane waves of the domain walls for most regions, up to some local dressing close to the location of the domain wall. Okay, so what I mean by this is that if we evaluate the corrections for the first few terms in perturbation theory, then we find that we now get some dressed version of the plane waves of domain walls, where these dx tilde consist of the original domain wall and some 1 over q squared suppressed terms, which, for instance, contain 3 domain walls. But there is some overall prefactor which is exponentially suppressed in the distance of these 3 new domain walls from the original one. And so as long as this is true, essentially the steps that led to this membrane formula all apply, and you still obtain that kind of expression. It's also useful to make some connection with previous discussions in random circuits, and also to understand this more intuitively. To look at the perturbation theory in the interaction picture instead of the Schrodinger picture that I've just described. And in this case, as I mentioned, so the interaction picture leads to some space-time diagrams where you have one domain wall that's initially propagating, and then it can split into three under the action of this 1 over q suppressed term. And then essentially there are two possibilities under further evolution. One possibility is that the three domain walls continue to propagate, or at some intermediate time they can combine and close together. Okay? And essentially you can map the contributions you get in the interaction picture to the Schrodinger picture. And essentially because in this first configuration I said that the energies are additive, so in particular the energy of three domain walls is higher than the energy of one domain wall, and we're doing some Euclidean evolution. So this configuration will be very suppressed. And the only important contributions are these kinds of diagrams. And on resumming them, you can see what contribution gives to the Renyi entropy, and gives precisely the same contribution that you get from first order in perturbation theory to the energy. Okay? So what this numerical dispersion relation that we found is doing is essentially resumming all possible diagrams like this and higher orders in 1 over q. Okay. Okay. So again, we were still in some restricted subspace because we had projected our Hamiltonian for general H alphas into the spin 1/2 subspace associated with the up and down spins. And if we consider the more general case, it's a bit harder to study because now we have a much larger Hilbert space dimension at each side. But we can make the statement that in this more general Hamiltonian, as long as the spectrum still has a gap and still has a one particle band of locally dressed domain wall-like states, then the membrane picture should still apply. And the membrane tension should, in all such cases, just be given by the Legendre transform of the dispersion relation. Okay, so this gives some interpretation of this membrane tension function at general velocities in some large class of systems. Right? And in particular, for this projected version of the Hamiltonian, we can use the dispersion relation curves that I showed on a previous slide and find their Legendre transform explicitly and get some membrane tension. And it satisfies all of these general constraints that I had mentioned earlier. Okay, and there should also be cases where the membrane picture breaks down, and this should happen in the set of models where you made some special choice of H alpha, so that in this P4 Hamiltonian, the gap ended up closing for some reason. You have some more intricate pattern of eigenstates. So in particular, if we made some choice of the H alpha is exactly like this transverse field Ising model, which can be rewritten in a free fermion form, then in that case, you find that you actually get a gapless Hamiltonian with a very different structure. You don't get a membrane picture. And the same is true if, for instance, we had chosen the H alphas to be consistent with some conservation law, like U1 conservation. Oh, okay, yeah, so this is something I did mention. So, so the Hamiltonian P4 that I get from projecting onto the up and down subspace is the same as if I'd chosen these H alphas to just be random GUE matrices which couple adjacent sites. And that is the case that we can do most explicitly. Okay, great. So any questions about this one-dimensional case?
So you said that the membrane picture has been applied to ADS-CFT where the gap is 0. How is it consistent with your last line?
So the gap that I'm referring to here is not in the actual Hamiltonian of the system, but in some kind of auxiliary, like n-copy or 2n-copy Hamiltonian, which is describing the entanglement dynamics. So it would be, so one would hope that there is some way of recasting the calculation even in like holographic CFTs to some form like this where you can derive some effective Euclidean Hamiltonian, but we don't, this has not been done and we don't know what that is. Okay. Good. So in In the higher dimensional case, the story becomes more complicated. But this is a case that we would really like to understand the membrane picture for holography, for instance, because due to the special structure of 2D CFTs, the membrane tension in ADS-CFT turns out to be somewhat trivial in 1+1 dimensions. Okay, so in 2+1 dimensions, if you look at the action of this P4 Hamiltonian, it essentially looks very similar to the one-dimensional action so this is some domain wall configuration. So the sigma labels a domain wall between downspins inside this region and upspins outside. And then at every point x along this surface, there's some probability that the domain wall gets moved outwards in the normal direction to x, and some probability that it gets moved inwards. Okay, and we have a collection, sum over such terms for every location x. So in this kind of setup, it's no longer easy to just diagonalize the Hamiltonian and explicitly find the eigenstates. But one thing we can try to do is just use this equation to try to derive some kind of differential equation for the evolution of the entanglement entropy of this region. Okay, and if you do this, then the evolution of the second Renyi entropy ends up taking this kind of form that you integrate along the surface some function gamma of the derivative of the entropy in the direction orthogonal to the surface. Okay, so this is not obvious, but in a few steps you can use this equation to derive such a differential equation. In this earlier paper, it was shown that once you have an equation of this form, then you can essentially, this is equivalent to the membrane picture with some membrane tension that is related to these to this gamma function. Okay, again, in saying this, I was neglecting certain interactions which can cause the domain walls to split in a few different ways into multiple domain walls. And once you have this, then like in the case of 1+1 dimensions, now you can associate the evolution of the domain wall with some kind of space-time diagram. And so the simplest diagram where the domain wall doesn't split just looks like this. And it would correspond to having a membrane picture with a membrane tension related to this gamma. But now we get some corrections which involve some space-time diagrams like these where the domain wall splits and can recombine and so on. And unlike in the 1+1D case, it seems that we not only need to take into account some interactions which renormalize the original membrane tension, like these ones, but in general, it seems that configurations where you split one domain wall into two and then never recombine should also be important in this case. Okay, so they don't, because essentially there is, it's no longer true in two spatial dimensions that the energy of two domain walls will always be higher than the energy of one domain wall. Okay, it's in the existing calculations for the membrane picture holography, such configurations don't seem to show up. It's not clear whether they don't show up at all or if it's because of the specific initial states that were chosen. So we need to analyze this more carefully. But essentially, understanding the membrane picture more explicitly in higher dimensions would involve an analysis of these kinds of diagrams. Okay, good. So that was most of my talk. Let me just quickly summarize. So in this talk, we found some general structure in Brownian models without conserved quantities, where the membrane picture turns out to be a result of some low energy modes, which resemble plane waves of domain walls. And some further things to understand are how this picture generalizes to the case of finite temperature. So this was all in the case without any conserved quantities. But if we include some conserved quantities, then actually we find that the picture doesn't generalize in a very straightforward way. There is more structure that needs to be understood. So this is something that we're currently trying to understand better. And then a more ambitious goal would be to understand how a similar set of modes will emerge in systems without any kind of random averaging. And one example of that would be the case of a holographic CFT, where we know that the membrane picture is true, so something like this should still hold. And then some further more vague questions are whether we can use, so these kinds of diagrams are also familiar from situations like analysis of the 3D Ising model, and there were some attempts to use these sort of string-like diagrams and and map this model to some kind of string theory due to Polyakov and others. I don't know how explicit such models are, but it would be useful if there was some connection there which could be used to understand this picture better. And then you can also ask whether there's some more direct connection between the set of low-lying modes that we found here and some effective field theories of hydrodynamics, which are developed in more conventional setups for, say, two-copy observables. So it would be nice to understand all that better. And thanks a lot for your attention. Yes?
I was curious about these membrane splittings that you showed in the end in your model.
Yeah?
Yeah. In the unitary quantum circuits, there's this nice theory that you can think of the membrane as some kind of extension of the mean cut prescription that sort of disentangles pieces.
Yeah.
Is that what's happening in this model as well? And if so, I was wondering if you have thoughts on how that kind of story could show up in the holographic context.
Right. So the way to make the connection to these min-cut type pictures more explicit. So now in this case, we have some continuous time evolution, so we don't quite have a circuit. But these diagrams are very similar to the kinds of diagrams you would draw in random circuits for the trajectories of these domain walls. And if you consider the case of just random unitary circuits, then you never have situations where one domain wall splits into multiple domain walls. But in principle, you could imagine a more general circuit model does have such splittings. And so, yeah, so all of these lines have exactly the interpretation of some domain, some min-cut through a tensor network in that sense. And then, yeah, similarly for these higher dimensional pictures, you can imagine them as cuts in a higher dimensional tensor network.
Any further questions? Well, if not, let's thank Shreya.